Hello students, in this class we will discuss about the second example on the Claisen condensation reaction. Now that is 2 moles of ethyl propanoate. So this is ethyl propanoate, CS3 CS2 C double bond O C2H5. Now this is ethyl propanoate. Ethyl propanoate. 2 moles of ethyl propanoate on reaction with the base sodium ethoxide Na plus OC2H5 minus. On reaction sodium ethoxide base, now that gives rise to beta ketoester. Now how to write the beta ketoester? CS3 CS2 C double bond O, and then here you'll have CH3 and then C double bond O C2H5. So this is a beta ketoester. Beta ketoester. And if you want to write the IUPAC name, see here, this is ethyl. See, this is the first carbon, second carbon, third carbon, fourth carbon, and then this is the fifth carbon. Ethyl hyphen. On the second carbon, you have a methyl group is there, ethyl 2-methyl. And then on third carbon, you have an oxo is there, 3-oxo. And then this is pentanoate. Pentanoate. So this is your beta ketoester. So you can write down the reaction like this, or you can write down like this. See here, this is CH3, CH2, C double bond O, C2H5. So this is the first mole of your ethyl propanoate plus, see, for the second mole, just separate this hydrogen on the alpha carbon. See, this is your alpha carbon of ethyl propanoate. Just separate this hydrogen and then treat this with your sodium ethoxide. So once you treat this with the sodium ethoxide as a base, then this undergoes loss of ethanol. See here, simply remove this ethanol and then write down the product as it is. So this is your CH3, CH2, C double bond O, and then write the product as it is. CH3 and then C double bond O, C2H5. So this is how you can write down the reaction. So you can write down in the examination like this or like this. Okay, then fine. Then again, this is a beta ketoester. Beta ketoester. Okay. Now let us go to the mechanism of this reaction. So the base abstracts alpha proton from the ester, forming a resonance stabilized carbanion. So what is the base here? See, this is your ester, CH3, and then CH2, and then C double bond O, C2H5. So this is the alpha carbon and this is your alpha proton. As I already told you, this alpha proton is acidic in nature. Why it is acidic in nature? Because it is electron withdrawing group. So this alpha proton is acidic in nature. Now, this is the base OC2H5 minus. Now the base will abstract the proton, forming a resonance stabilized carbanion. Okay, so now you'll get a carbanion first, CH3, CH minus, C double bond O, C2H5, plus you'll get ethanol here. So now you have a conjugation, p-pi conjugation here. You can write down the resonance structure for this. So this is a p-pi conjugation. Remember that this is a p-pi conjugation. So you can write down the resonance structure for this. This is CS3, CS double bond CH, O minus, and then this is O C2H5. Now this is what we call it as an enolate ion. Enolate ion. So this is the first step. So this is the resonance stabilized carbanion. This is the carbanion, this is the enolate ion, right? And in the next step, see in the next step what happens is, now this is the second mole of your ethyl propanoate, CH3, CH2, C double bond O, C2H5, plus you have the second mole of your carbanion. See, this is second mole of your ester, second mole of ester, and this is your carbanion. This is the carbanion formed in the step 1. Okay. Now this undergoes a nucleophilic addition. This undergoes a nucleophilic addition. How to write this nucleophilic addition? See here, you know that oxygen is more electronegative than carbon. So the pi electrons are shifted towards oxygen. The carbon becomes deficient. And then the carbanion donates lone pair of electron to this deficient carbon. So as a result, you'll find a carbon-carbon bond between this carbon and this carbon. Okay. So now see the product. So this is CH3, CH2, CO minus, and then OC2H5, single bond, CH, CH3, C double bond O, OC2H5. Now I already told you that this is what we call it as a tetrahedral intermediate. This is a tetrahedral intermediate only. And then as already this is what we call it as a new carbon-carbon bond formed. New CC bond formed. This is the new carbon-carbon bond formed. Now this undergoes an elimination reaction. See here, this undergoes an elimination. Elimination of what? Elimination or removal. You can call it as removal or elimination of this ethoxide ion. See here, this is the leaving group. Once this is the leaving group, carbon becomes deficient. Now oxygen donates lone pair of electron to this deficient carbon. So you will get CH3, CH2, C double bond O, and then CH, CH3, C double bond O, OC2H5. You have got the beta ketoester. See here. You have got the beta ketoester, but this beta ketoester is formed in low yield. So this is formed in low yield because the equilibrium is not favorable. So this is formed in low yield. So this is the product. This is the product in the step 2 of this mechanism. Plus you have got OC2H5 minus. Now see here, if you observe carefully, as I already told you, see here, this is an ester. This is an ester and this is the product. This is the nucleophile. See, this is nothing but a nucleophilic substitution at the sp2 carbon. That is what is called your acyl carbonyl group. This is acyl carbonyl group. A nucleophilic substitution at the sp2 carbon which involves nucleophilic addition followed by an elimination. So therefore always remember that the nucleophilic substitution at the sp2 carbon involves nucleophilic addition and elimination reaction. Okay, so this step is what we call it as an addition elimination step, right? So this is very important. This step is very important. Then what happens in the next step is that, so you'll have an acid-base reaction between this beta ketoester, CH3CH2, C double bond O, and then you have hydrogen here, and then CH3 here, CH3, C double bond O, C2H5. Now this is your beta ketoester. This beta ketoester is a strong acid. This is a strong acid. Why it is a strong acid? Because this particular part is an electron withdrawing group. This particular part is an electron withdrawing group. Now this CH is in between two electron withdrawing groups. So therefore this hydrogen is highly acidic in nature. And therefore this is what is called active methylene group is also. So this is also called active methylene group, and this particular hydrogen is highly acidic in nature. That's fine. And then here you have a base, which is your ethoxide ion. Fine, this is a strong base. Now this is an acid-base reaction. So once this acid-base reaction takes place, this ethoxide ion abstracts this hydrogen, forming again a carbanion. So this is CH3, CH2, C double bond O, and then CH3 minus C double bond O, C2H5. See, this is a C double bond O, C2H5. Plus you are getting an ethanol. Now this ethanol is removed by distillation. This is removed by distillation. So once this is removed by distillation, then the shifts towards the right, towards the formation of the carbanion. Now this carbanion is now hydrolyzed in the presence of an acid. Once you hydrolyze in the presence of an acid, then see here, now this is protonated. So once you protonate this, now here you'll get CH3, CH2, C double bond O, CH, CH3, and then C double bond O, O, C2, H5. So this is your beta keto ester. Now this is the beta keto, final product of this beta keto ester. Now this beta keto ester is formed in very good yield. This is formed in good yield. This is formed in good yield. Because once this ethanol is removed by distillation, equilibrium shifts towards the formation of the carbanion, which on protonation gives your beta keto ester. So this is how the reaction takes place with ethyl propanoate. I hope it is very clear to you. Just go through these steps. See, first step is the formation of a resonance stabilized carbanion. And then see here, you can also write down the mechanism with the inlet anion if you want. You can write down the carbanion, or if you want, you can also write with inlet ion. Fine. The step 2 is an addition elimination step, which is a very important step. So the carbanion undergoes nucleophilic addition with the second mole of the ester, followed by an elimination gives beta keto ester. But this is formed in a low yield here, and therefore the third step is an acid-base reaction between the ethoxide ion and then the beta keto ester. So to give you the carbanion and then ethanol. Once this ethanol is removed by distillation, then this carbanion on hydrolysis will give you the beta keto ester in good yield. So as soon as ethanol that is formed is removed by distillation, the equilibrium shifts more towards the right hand side, towards the formation of the carbanion, which on hydrolysis gives beta keto ester. So this is how the reaction takes place. Okay, then next step. Now this is a homework to you. So write down the mechanism for the Claisen condensation reaction between 2 moles of ethyl pentanoate in the presence of a base sodium ethoxide. So write down the structure of ethyl pentanoate. So this is CH3, CH2, 1, 2, 3, 4, and then this is your pentanoate, OC2H5. Okay, so this is your ethyl pentanoate. So this is 1, 2, 3, 4, 5. Ethyl pentanoate. This is ethyl pentanoate. Now this on reaction with the base NaOC2H5, that is sodium ethoxide. Now see how to write down the product. See here, this is CH3, CH2, CH2, CH2. First write C double bond O and write the alpha carbon of the next mole of ester. Just write this alpha carbon of the next mole of the ester. CH double bond O, OC2H5. See here. This is the alpha carbon of the next mole of the ester. This is alpha carbon of the next mole of the ester. And from here you write the remaining carbons. So 1, 2, 3, 4, 5. So this here, this is the new CC bond that is formed in the reaction. That is the new carbon-carbon bond formed in the reaction. New carbon-carbon bond formed. So this is alpha and this is beta. So therefore this is your beta keto ester. Okay, now you write down the mechanism for this reaction. So this is very simple. I hope you can do it very easily. Then crossed Claisen condensation reaction. So crossed Claisen condensation reaction is a condensation reaction between two different esters in which one ester has alpha hydrogen and the other ester has no alpha hydrogen. See, for example, here I'll just give you the example of see, this is ethyl benzoate. This is ethyl benzoate. So this is your ethyl benzoate. Now this ethyl benzoate has no alpha hydrogen. This has no alpha hydrogen. Ethyl benzoate has no alpha hydrogen. Now on next one is ethyl acetate. See here, for ethyl acetate I am just separating this hydrogen for the sake of convenience. This is ethyl acetate. Now ethyl acetate has no alpha hydrogen, and ethyl acetate, see this is ethyl acetate. Ethyl acetate has alpha hydrogen. This has alpha hydrogen. This has alpha hydrogen and can form, has alpha hydrogen and can form a carbanion. It can form a carbanion. Now this on reaction with your base C2H5O minus and A plus, you treat with sodium methoxide. Just remove this ethanol. Just remove this ethanol and write down the product as it is. Now this is your C6H5, C double bond O, single bond CH2, and then C double bond O, C2H5. See, this is a beta keto ester. Again, this is a beta keto ester. So here there are only 3 carbons are there, 1, 2, 3. These only 3 carbons are there. So ethyl propanoate. Now here you have to write like this only. Ethyl. See here. Now this is 3-oxo, 3-phenyl, 3-oxo, 3-phenyl propanoate. So this you have to write in the alphabetical order, OP. So this is oxo is there and then phenyl is there. So ethyl, 3-oxo, 3-phenyl propanoate. So this is the IUPAC name of this. Now let us write down the mechanism for this crossed Claisen condensation reaction. Now this is a very simple. Now step 1 as usual. Now these steps I already told you. See here. Now the step 1 is the CH2H and then C double bond O C2H5. Now this is an acidic proton. This is acidic, and now you have the base sodium methoxide. Now the base will abstract the proton, forming a resonance stabilized carbanion. Now this is CH2 minus and then C double bond O C2H5 plus you'll get ethanol. So this is a resonance stabilized carbanion, right? So you know already we have discussed about this resonance structure. So therefore you can write down the resonance structure very easily. Where you have a p-pi conjugation is there. And this is what we call it as an enolate ion. Enolate ion. Next step 2, of course, you know that it is a nucleophilic addition elimination step. And then finally hydrolysis, nucleophilic addition elimination step. Now this carbanion reacts with ethyl benzoate. Now this reacts with your ethyl benzoate. So this is C double bond O C2H5 ethyl benzoate. This is ethyl benzoate. Plus you have a CH2 minus C double bond O C2H5. Okay. So this is a nucleophilic addition. As usual, this is a nucleophilic addition. A nucleophilic addition will give you a tetrahedral intermediate. So this carbanion, see here. See here, oxygen is more electronegative than carbon. Pi electrons are shifted towards oxygen, and then carbanion donates electrons to this deficient carbon. So you get a CC bond, a new CC bond. So this is your C O minus, and then O C2H5, and then see this is the new carbon-carbon bond formed, C double bond O C2H5. Now, as I already told you, this is your tetrahedral intermediate. Tetrahedral intermediate. Okay. Now this undergoes an elimination. So this is an elimination step. This is lost. Once OC2H5 minus is lost, this carbon becomes deficient and oxygen donates electron to this deficient carbon. Over. So this is your C6H5, C double bond O, and then you have CH2, C double bond O, C2H5, plus you have OC2H5 minus. So this is a beta keto ester. And as I already told you, this is formed in a very low yield. And then next, step 3. Step 3 is an acid-base reaction. So C6H5, C double bond O, and then, so just write hydrogen here separately, CH2, C double bond O, O, C2H5. See, this is a beta ketoester. This is alpha carbon, this is beta carbon. Now this beta ketoester is a strong acid, as I already told you. And then now you have a base, that is your ethoxide ion. Now the ethoxide ion will abstract this hydrogen. This is a strong base. And then this base will abstract the proton. And then you'll get a carbanion. C double bond O, CH minus, and then C double bond O, O, C2H5. Plus you'll get ethanol. Now this ethanol is removed by distillation. So once it is removed by distillation, then this equilibrium shifts more towards the formation of the carbanion, and then this carbanion on hydrolysis. Now this on hydrolysis. See how I'm writing the hydrolysis step. Once you have a positive charge, this is a protonated form of an acid. This is a protonated form. So once you have a positive charge here, electrons are shifted towards the positive charge, and this becomes H plus, and the carbanion donates electron to this deficient hydrogen. So you'll find a bond between carbon and hydrogen. Over. So your mechanism is over. C double bond O CH2, and then C double bond O C2H5. Over. So the beta ketoester is formed in good yield. Over. Then I'll give you a homework. Now this is a homework to you. This is a homework on crossed Claisen condensation reaction. Example 2. So you take here this is ethyl formate. Ethyl formate. What is the IUPAC name of this? The IUPAC name is ethyl methanoate. Only one carbon is there, so it is called ethyl methanoate. Plus you write CH2H ethyl acetate, CH2H C double bond O C2H5. So no alpha hydrogen in this case. No alpha hydrogen. So this ethyl formate has no alpha hydrogen. Ethyl acetate. See, this is ethyl acetate. Now this has alpha hydrogen and forms a carbanion. Now see here. Now treat this with sodium ethoxide. Remove this ethanol and then write down the product. And this is, I see, I gave you the reaction, I gave you the product, and then the only thing is you have to write down the mechanism for this. So this is a beta keto ester. Just write down the mechanism for this particular reaction. Okay. Now here, and finally, so note. I'll just give you a note only. What is this note? Note. What is this note? See, let us suppose you have. See, this is your second mole of the ester. This is the second mole of your any ester, second mole. And then here you have a carbon. You have CH3 double bond C O minus OC2H5 only. See, this is your inert anion. So what I am trying to tell you is that here I'll just write down the mechanism with the inert ion. How to write down the mechanism with inert ion? Okay. If you want to write the mechanism with inert anion, then what you need to do is that okay. Now see here, you know that oxygen is more electronegative than carbon. Pi electrons are shifted towards oxygen, this carbon becomes deficient. Once this carbon becomes deficient, see here, these pi electrons are donated to this deficient carbon. So once the pi electrons are donated, this carbon becomes deficient. And then this oxygen donates lone pair of electron to the deficient carbon. See here, what is the difference? What is the difference? The difference is you have to write two arrows here. Once you write the mechanism with inert anion, you have to write two curly arrows. But once you write the mechanism with only with the carbanion, see here, once you are writing with the carbanion, you have to write only one curly arrow here. But once you are writing with the inert anion, you have to write two arrows. That's it. That's only the difference. And remaining steps are all same. CS3CH2, C, O minus, and then OC2H5. From here you have CC bond that is formed, CH2, C double bond O, OC2H5. And the remaining, this is only tetrahedral intermediate, and then elimination, this is nucleophilic addition, and then elimination. In the remaining steps are all same, and no change at all. The only thing I'm explaining you is how to write the mechanism with this inert ion. That's it. See, this is how you have to write it. Fine. So now we have discussed two examples. So far we have discussed two examples on Claisen condensation reactions, and then I gave you one homework, and then two examples on crossed Claisen condensation reaction. In the next video, we'll discuss about the intramolecular Claisen condensation reaction in the next video. So thank you very much.